In our previous video, we talked about electronegativity and how it affects whether a bond is polar or non-polar. Okay, and now this video we're going to talk about how you determine the shape of a molecule, and then that's going to lead to the idea of is the molecule polar or non-polar, like we discussed at the end of our last video. Okay, so when you draw a molecule that has more than 2 atoms in it, what you can do is you can determine what's called the shape, or what's called the molecular geometry of that molecule. Okay, and the way that you determine that is based on what is called the valence shell electron pair repulsion theory model. Okay, sometimes you just pronounce it VSEPR, even though I know the S comes first before the E. Typically people pronounce it VSEPR. Okay, and VSEPR is the idea of if we could see these molecules, what shape would they actually be in? How would the atoms be arranged around the central atom in this case? Okay, and the way that you determine the shape of a molecule is you do that based on the number of bonds and based on the number of what are called the non-bonding or the lone pairs on the central or on the atom in question. Typically it is the central atom. Okay, so as you can see here, there are 6 different shapes that you need to know and that you need to be familiar with. So I'm going to go over each of them, and after we go over them, then we're going to look at these and look at our examples here. So the first shape we're going to look at is a molecule, and again, this is the really important part right here, is the number of bonds and the number of lone pairs the atom has. For example, every single molecule that contains 2 bonds and no lone pairs has a linear shape. Okay, now in terms of when you're talking about the number of bonds, like notice right here, there's a double bond there. For doing this, a double bond or a triple bond still just counts as 1 bond. So in this case here, in the NO2, there's just 2 bonds, 1 double bond, 1 single bond. Okay, so when you draw a Lewis, so the first thing that you do is you always draw the Lewis electron dot diagram. Once you have that dot diagram, then you count the bonds that are made to that central atom, and then you count the number of non-bonding pairs or lone pairs on that central atom. Okay, and if there are 2 bonds and no lone pairs, then it is a linear shape. And as you can see here, the bond angle between the outer atoms is 180 degrees. So let's say, for example, I ask you to draw the CO2 molecule, and you draw it, and after drawing it, you get this right here. Okay, and that's where you go, okay, on the central atom, the carbon, how many bonds are there? There's 2 bonds. And how many non-bonding pairs or how many lone pairs, again, are on the carbon? We're not talking about these lone pairs. Those are lone pairs, but those are not on the central atom. Okay, how many lone pairs are on the central atom? 0. So 0 lone pairs. And you go, oh, if it has 2 bonds and 0 lone pairs, that is a linear shape. Okay, which basically means it forms a line. Okay, and that line that it forms is again, obviously it has a bond angle of 180 degrees between those outer oxygen atoms. Okay? All right, the next one that we need to be familiar with is one that has 3 bonds, and again, no lone pairs. So 3 bonds and no lone pairs is, for example, the BH3 molecule. Okay, notice that there's no dots on the boron, no dots here at all. Okay, but there are 1, 2, 3 bonds. So this can't be linear because linear can only have 2 bonds. Okay, so this one is what we call the trigonal planar shape. Okay, so I'm on a website now that is called PHET, P-H-E-T. You can see that up in the corner there. If you go onto Google and just type in P-H-E-T, PHET, and then molecule shapes, it'll take you to this website here. And what I'm doing here is I'm just showing you this is the shape of that molecule. And you notice that as I move it around, it might move a little, the angles might change a little bit, but once it finally reestablishes itself, you'll notice that the bond angles are 120 degrees. Okay, you'll also notice that it's flat. Okay, and notice the way that I have it right here. It's a flat molecule, but when I rotate it this way, it does form, if you take the outsides, it forms a triangle. Okay, and so you'll notice the name of that is called a trigonal planar shape. If something is planar, like the Great Plains in America, it's a very flat part of America. So it's a flat triangle, so it's referred to as trigonal planar. Okay, and again, those bond angles are 120 degrees. Okay, wait, do we have to remember this stuff? Anything that I teach you, yes, you have to remember. Do we need to remember that it's trigonal planar? Yes. Do we need to remember the bond angles? Yes. Are 120 degrees? Absolutely. Okay, the next one. Notice it's kind of similar. Okay, but now it only has two bonds, kind of like a linear one, but it has one lone pair. So let me switch back here to this. So what I'm going to do is I'm going to notice up here in the corner you can remove bonds and you can add lone pairs. Okay, so notice here that what we've done here is notice that the shape of the molecule is the same. It's still a trigonal planar shape. We've just taken one of those bonds away and we've replaced it with a lone pair. Okay, now they do say that that is a 120 bond angle. These are just the models. Okay, if I go to a real molecule here, oops, I went back a little too far there. If I go to real molecules here, maybe real molecules, and I find one that has two bonds and one lone pair, which is SO2. If I show those bond angles, notice that the bond angle is a little bit less than 120. Now you don't need to remember that number. Even notice in the notes that when I say it, I don't say 119. I say, it's a little, that means less than. Okay, a little bit less than 120 degrees. Okay. Now, why does that happen? Okay, it's because this lone pair right here is not tied to a bond. It's not stuck to a bond. And remember, electrons repel each other. So these electrons right here basically can repel. They push against that bond just a little bit and moves that bond a little bit closer together. So this angle, instead of being 120, it's a little bit less than 120. Okay, and it's almost like we took a linear molecule and what did we do to it? We bent it. Okay, and that's why it is called a bent molecule. Okay, all right, so that's half of them. We've got linear molecules, we've got trigonal planar molecules, and we have bent molecules. Okay, now the last three are all based on this one right here. Okay, if you have 4 bonds and 0 lone pairs, okay, what you have is something, and I can keep using real molecules here, is you have this molecule right here. Okay, let me rotate it here a little bit. Okay, now this one's a little bit harder to draw because it's in 3D. And notice on the computer screen you can see it pretty well. But notice that basically, like this one's basically sticking straight up. This one's coming to the side. But this one right here is kind of sticking out towards us, where this one back here is sticking into the screen. Okay? So notice that if you were to put sides on that, that would have 4 sides. Okay? And that is why it's called a tetrahedral. Okay? If you think of the video game Tetris, Tetris is made up of a bunch of 4-sided figures. Okay? And so that's why it's called a tetra, means 4 again, in real life. Okay? So, anytime you have 4 bonds and no lone pairs, it is a tetrahedral shape. The bond angles, again, kind of weird. This is the one weird one that you have to remember, is 109.5. Okay, and these lines right here, what they're trying to do here is remember that one is sticking out and one is going into the screen. That's what they're trying to show on a 2-dimensional piece of paper, is they're trying to show that. But do you have to show that? Of course you don't. I would never. If I were to draw CH4, you know how I draw it? I draw it exactly like this, CH4. And then if I say, what's the shape of CH4? I would say it's tetrahedral. Okay, and then if somebody says, what's the bond angle? I would say 109.5. Okay, now be careful here. Because, well, wait a minute, no, look right there, Johnson. It's 90 degrees, I can see it. That's just the way that I drew it, okay? The way that you draw, I mean, think about like our previous example up here of CO2. What if I drew CO2 like this? Does that mean that CO2 is bent? No, that's just how I happen to draw it. CO2 is absolutely a linear molecule. You can draw these Lewis electron dot diagrams with whatever angles you want, okay? But the real angle is based on the number of bonds and the number of lone pairs. Okay, this absolutely is a tetrahedral shape, even though I drew it like it's on a flat 2D surface. The bond angles absolutely are 109.5 degrees. So again, notice here, let me go back to our drawings here. Let's go back to the models. Notice that again, if I have those 4 bonds on there and I show the bond angles, that is a tetrahedral shape, as we can see there. Now watch as I take a bond away and I add a lone pair. Notice what happens. Not much. Okay, notice that those, it's still the same shape, except that one bond that was going up is no longer there. That can really help you in trying to remember all 6 of these. That this 3 and 1, if you add 3 and 1 together, you still get 4. That's still a tetrahedral shape with one of the bonds now missing. Okay, I can even make it, watch here, where basically down here, see where it says electron geometry? That just means if all of the bonds were there, what shape would it have? Of course, it's going to say tetrahedral, of course. Okay? But in terms of what's the real shape of the molecule, what's the geometry of that molecule, it is what we call a trigonal. Okay, so let me kind of show you here if I can rotate it the right way. Notice that if I rotate this, it's still a triangle. Okay, but now it's not a flat triangle, it's a triangle that you can see kind of goes up. Okay, and so what they call that is they call that trigonal because it's a triangle, but rather than planar, we call it trigonal pyramidal because it kind of goes up to form a pyramid. Okay, and those bond angles, again, if it were tetrahedral, the bond angles would be exactly 109.5, but because of that one lone pair, it's going to be a little bit less than 109.5. Okay, and then our last one here has 2 bonds and 2 lone pairs. So again, 2 plus 2 equals 4. That again is still, in terms of the electron geometry, I'm going to take another bond away and I'm going to add another lone pair. Notice the bond angle, still 109.5, so it's still a tetrahedral shape. Okay, but now it has 2 lone pairs rather than just the 1. Okay, and so you can see that similar to the other molecule that was like this, that one was bent and this one is more bent. We've taken that linear molecule and bent it even more because there's 2 lone pairs on it rather than just 1. And again, that bond angle is significantly less than 109.5. Well, how much less? Well, again, let's go back over to our real molecules. So CH4, which is a tetrahedral, is 109.5. Okay, NH3, which again also is a tetrahedral with 1 bond taken away. Once I go to real here, what happens? It drops down to about 107.8. And then if I put 2 lone pairs on there, which is what water is, notice it drops all the way down to 104.5. Okay, so every time you take a bond away and you replace it with a lone pair, the remaining bonds always get a little bit closer together due to that increase in the electron repulsion. Okay, now you don't have to remember 107.8 or 104.5. All I want you to remember is the original one is 180, 120, and 109.5. But as you take bonds away, those bond angles do get a little bit smaller.